Hi there. Welcome to the Productive AI podcast, where we aim to simplify AI and make it more accessible to business leaders. I'm your host, Troy Angradon. On today's episode, we're going to be talking with Jags Kandasamy, who is CEO of Latent AI, about why AI needs to be able to run out at the edge, which might be a factory, a car, or a ship, or many other places, what the issues are in pushing AI out to the edge, and what they're doing to make this simpler and faster so that companies can improve their time to market with these edge AI applications. So, Jags, thanks for being on the show. This is great. I've been looking forward to this. Can you tell me a little bit about just your background, how you got involved in this? Because I know you've been an entrepreneur before and have a long history in tech. So how did you get here?
To give you a background, I started my tech career 21 years ago, started selling computer-based tutorial software, and then moved into financial tech and others. Right? To get to Latent AI, I'll have to start maybe a few years before starting Latent AI. I was running a startup called AutoSense. At AutoSense, we had automated human hearing. What do I mean by that, right? Our software could listen to any sound, not just human sound, any sound, and be able to categorize, classify, and identify what was going on there. And we had moved that software to predictive maintenance use cases in the factory floor, aircraft, and automotive side, right? You know, a good mechanic always listens to sound before even he opens his eyes, right? That's the use case that we went after, and we went after the industry 4.0 applications of like, okay, can we gather the retiring technician's hearing ability and encode it into the software, right? That's where we started. One thing we quickly realized there was like, you have a sensor listening to the sound, and you have this nice server sitting in the cloud. There's a lot of miles in between, right? And a lot of cabling that goes between. You cannot send, and we quickly realized, like, you record sound and you're sending every minute, every second of the sound up to the server. It is not scalable, right? Our wireless bill started to mount up, and we realized this is not going to be a successful business model. So that's where the first, right in the hit me in the middle of the eye was, oh, we got to do something in moving some of the processing towards the where the machines are. We didn't know what was called the edge then, but we started to realize, okay, we need to put some computing over there. So we looked at the application and tried to compress some of the models that we were doing and push it onto small devices that ran on the edge. Company got acquired by Analog Devices, but the fire was still there, right? And edge was just then picking up. I joined SRI International as an entrepreneur in residence to look for technologies that could help me achieve this and solve this problem at the edge. And I came across the technology for Latent AI and spun the company out in December of 2018, and here we are.
That's awesome. And I love hearing Genesis stories like that, where you're working on one problem and then in solving that problem, you kind of identify a larger opportunity. And basically, you guys were edge before edge was cool. All right, let's talk a little bit more for people who are not really familiar with the concept of the edge. What could that mean in terms of applications, devices, locations, and maybe even industries? Can you give some broad examples just so somebody can get their head around what does it even mean to say I'm doing compute at the edge? Forget AI.
Definitely, right? Like maybe start with the small anecdotal data here. All of the internet in 2002 was 22 zettabytes. Oh, no, 22 exabytes, sorry. 22 exabytes. Today, in 2020, we produce that data in 4 hours.
Wow.
Right? And imagine in 2002, .com was in full bloom, and we had a lot of computing then, and we thought we had achieved massive computing power. But we couldn't solve that problem then. And with 22 exabytes being produced every 4 hours, you don't have the prayer to solve this, right? And most of the data today, and we've seen this big data concept explode over the last few years, then public cloud came out and all of this going on. And everybody said like, oh, bring all the data into the cloud and we can do all the processing and we'll give you insights and we can do that and we can do this and stuff. But if you ask CIOs today, 90 to 95% of the data that they've collected, nobody has touched. Not even a single query run, not a single analytics run on that.
Wow.
Why do you collect that data when you're not using anything else?
Right.
So this is where edge comes into play. Think of edge as your first layer of filtering, right? Think of this as like multi-layer sieves, right? You got the big sieve, the smaller sieve. You go through, you can filter out all the relevant and required stuff and take out the gunk as it passes through. Right? Edge comes to play right there, right? Now, everywhere we are putting sensors. Semiconductor has gotten so cheaper that we are making 10 cent, 20 cent sensors out of this. And each one of them is converting analog to digital data. That analog to digital conversion used to be very, how do I call it? A human intervened sensors, right? You had to go sit in front of a computer, type something. That's how you converted your thoughts into keyboard, into digital information. Or you took a camera, you clicked it, you snapped a picture, right? That's how you converted things. But today, all of that analog to digital conversion is happening autonomously, automatically, right? Without any user input. All of this data is coming up. So this is where you need to put compute and processing power closer to where the data is getting originated. So you can discard that 95% of gunk out and take that 5% signal that you need to worry about, you can drive business value out of, and then pass it along the chain. And you can store that as you, or the inferences or the intelligence that you get out of it, you can store it for further use.
Okay, and that's a great starting point. And so example wise, I did a lot of work in the wearable space, looking at things there. And let's use the example of an Apple Watch or anything that's a wearable on the wrist, where it's collecting a whole bunch. It's collecting your heart rate, and maybe it's collecting other things, or it's calculating things like your HRV, heart rate variability. And but they're often collecting a lot of analog data, and it's noisy. And you don't want to send absolutely every sample of that data all the way back up to whatever cloud or data center. So they're very much acting like a filter, like you said, where they're filtering, they're taking out the noise, they're boiling it down to the bare essentials, and then they might just send one little data point up to the cloud that would be, this was the heart rate for this last second, or for the last 10 milliseconds or 100 milliseconds, something like that, as opposed to every millisecond. So they sort of reduce and average the data and send it up. Is that kind of an example of what you're talking about?
That is a great example, right? And then maybe if we switch to the most heavier volume stuff, which is video cameras, right? We have CCTV cameras everywhere. Everybody in their house has got a surveillance camera, a security camera, right? A Ring doorbell, stuff like that. So think about it, right? If we look at that, anybody that comes in and goes, a motion triggered, you start to collect the footage, 10 seconds, 12 seconds, whatever the timer that you've set, you collect that and you send it up to the cloud. I had an advisor that was telling me that it has a doorbell camera. He was getting 120 alerts within the hour. And he was like, what the hell is going on? And he went to check it out. It was a bee
buzzing around the camera.
Buzzing around the camera. He thought it was a hole. The camera was a hole and he was trying to enter it.
Yeah.
Every time he did that, it was triggering an alarm.
Yeah. So
this is where, right, like if you don't put intelligent processing right there, you're getting unwanted feeds. Right?
Yeah, absolutely.
False positives all over the place.
Mm-hmm. And I looked a lot at the camera space, the home security space, and absolutely you see, I think some of the early players were like, hey, we can do human identification and various things. Animal car person is kind of the most common. But a lot of that was, as you said, they were actually just saying, okay, first there's motion. So now we're going to record. Now we're going to take the 10 seconds. We're going to upload it to the server, and the server is going to make a determination or classification, animal or person or car, and then it's going to send it, or nothing, and then it's going to send it back. And so you have this long feedback loop, and you're sending a lot of data. up to them. And I know there were a number of these camera manufacturers who were then saying, okay, we can finally do it on the camera. So we can make that determination. You have a human or a car or a package or whatever, and they're able to do that. Essentially, what you're talking about is enabling that, right? Enabling providers like that to put that intelligence right on that camera.
Exactly.
Okay.
Exactly. So we are actually, this is hot of the press, right? So we just finished working with the semiconductor company that has the lowest power AI accelerator chip, right? In sub-milliwatts, you can talk about per inference, right? These guys have always on chip that's looking at the camera, and it'll only act if there is a human present. It acts as a wake-up word, like, as you're calling out your voice assistant's name, right? Similarly, if there's a human present in the frame, then the activity starts.
Got it.
So you're removing a motion sensor, an infrared sensor. You can run with the same power on a visual camera. Right? We are enabling, our software is enabling them to bring the model to do that on their chip.
Okay. That's awesome. So I think that gives people a good idea. And of course, there would be a million of these wearables, smartphones even have AI and kind of neural engines in them these days. Smart speakers could be something at the edge, relatively speaking. Our Roomba could be at an edge device. Essentially, it has some smart intelligence that maps out the house and says, I'm gonna not clean by the dog food bowl. So all of those would be good examples, right?
Yes,
okay.
There will be. The whole idea is how do you also, like from a consumer electronics perspective, how do you maintain your privacy too?
Right.
None of your raw data is going out to the cloud for somebody to hack into. Right?
Yes.
All the companies are collecting with good intention, right? We want to learn more about you, learn more about what you're doing so we can provide you a better service. Very noble intentions.
Sure.
But then the hackers don't have that noble intention. They come in, I got this information. What can I do?
Yeah, so I have a 24-hour live feed to 10 cameras in this house and every other house on this block. Absolutely, it's a huge attack vector. So if you get rid of the vector by saying, we're not going to let that footage leave the house, that's obviously the better solution. Leaves less surface area to attack. So how hard is it for these companies that, let's just use the camera example, for a company to say, we're currently processing everything in the cloud, but we want to put all of this intelligence in a robot, in the house or a camera or whatever it is. How hard is that for them to do? Because it seems like they struggle with this and it takes them years to get these products to market.
Absolutely.
What's the
issue? This is one area of, from an AI perspective, deep learning is very, very old and new at the same time. Right? These models that we're working on the convolutional neural nets, these were all defined in the 90s. Right? Now we are getting a lot more effort into it and a lot more research going into it because of the advent of compute. We've got more availability to compute, more availability to data. All of this is the problem that models have themselves is that they are larger in size. A simple model will have at least a couple of million parameters to work with. Right? If you have a couple of million parameters and each one of the parameters is expressed in floating point, 32-bit floating point, trying to do the compute on that is hard math problem in itself. And these models were defined and they took off because of GPUs. And you could not put a GPU on an edge device. Right?
Just surely because of cost and power.
Cost and power, both.
Okay. Right. So these models, size-wise, is it a storage problem or is it much more just a compute capacity problem?
It's both.
Okay.
It's both storage and compute. Right.
Okay.
So you're looking at
cost.
If you have therefore cost, it increases your how much cache do you build into this?
Right.
Can I put a gig cache or do I need a 10 gig cache in there? Right. Even the semiconductor is cheap, but the moment you start to add things up, even a penny is going to cost you $10 down the road.
Right.
When you start to package things up.
So when you're building these systems, especially in the factory floor, or you're doing this predictive maintenance, let's go back to kind of the genesis of all of this work that you guys were doing. What were your big sort of aha moments where you said, okay, clearly this stuff doesn't we can't send it back. We can't send it across the mobile networks. It's too expensive. That was one that sounds like a big aha. And the second was we have to keep doing it somehow, so we have to move it closer to the actual workflow, in this case, the factory floor or the oil derrick or whatever. What other sort of key insights did you have about the problem space and this potential solution space?
The latency effects. For example, one of the customers that we were working with was an automotive tier one supplier. They were making chassis for the Detroit companies, right? Car chains. They have this large industrial press that was doing about 25,000 tons weight, right? They were stamping out steel parts. One of the things that they said was like, when the pressure on the brake pads, if they get weakened, the press is going at 25,000 ton every few seconds. In that mode, when it hits, it has to brake, release the brake, come back up, release the brake, go back down. So if the brake slips even by a millisecond, it has the opportunity to collapse the press onto itself. Imagine 25,000 steps, 1,000 ton collapsing on itself.
So the machine, if it's out of sync, can destroy itself.
Destroy itself, exactly.
Wow.
Right? Now, we were listening to the brake pads. Basically, the brake pad engagement is a sound, right? The longer it takes means the brake pad is thinning out. You should be able to change the brake pad without visual inspection because it was inside a magnetic container and stuff. So we were listening to it. If the brake pad is wearing thinner and thinner, you should be able to change it before it goes out and causes the machine to break down. If we find this information, we say like, hey, I think it's ready to change in this cycle now, and stop it and change it instead of waiting, go around and like, oh, cloud processing, and then the next day you get the report, the machine might be dead. Right? That instant feedback, sending it to the PLC and saying like, stop the machine, inspect,
right,
and replace.
And I think that what's interesting is that predictive maintenance in factories and oil and gas and a number of different areas, manufacturing and various things, it seems to be a really ripe area for AI, because traditionally it seems like, and correct me on this, or if you've got a bigger, better picture of this, but it seems like traditionally the issue has been, we know that on average each of these machines will fail. Mean time between failure, right? That's a well-known statistic for each machine. We know the average time of failure. We just don't know which machine is going to fail. And so we just replace everything on a certain cycle, and you end up incurring a whole pile of preemptive or preventive maintenance that you may not need to put in. And the only other way to deal with that is to visually inspect, or have humans inspect it, and that is sometimes too expensive. So they're kind of caught in this bind, and AI seems to fit right in the middle, where it says, why don't you stretch out your maintenance schedule, but if we see something that is actually about to fail, we'll notify you, and then you can just fix that. That's basically what you were doing.
That's exactly right. That's exactly what we were doing, right? So if you look at this particular braking example, because it was in an enclosed container, they just had a 60-day window or a 30-day window that they would just go open it up, replace the brake pads, and go.
Right.
Because the machine was it was a high-value asset.
Right.
And the plant manager showed me the brake pads. And he said, like, look at this. This is a new one, and this is a used one. I'm like, it looks new. Like, yes, it is. We used 3% of it before we changed it.
So they have they used 3%, and so their room for error room, I guess, is so huge. Basically saying, we'll use 3% and we'll throw it away. We'll put a new one in. It's a renewable part, and it's worth it for the cost of the machine.
Exactly.
Wow.
Because that machine was non-operational for 45 days out of the 60-day cycle. Because they were doing some other maintenance and construction around it, so they didn't use it.
Right.
The preventive schedule was 60 days. Every 60 days, somebody opens it up, replaces the brake pad, and moves on.
Right. Excellent.
So
well, that's a great
what
example.
They're trying to avoid. That it's an expensive part. It's not a cheap part.
Right. So, what before we leave this sort of the aha and the key insights, were there other companies that were trying to solve this problem and shipping, computers and technology to these factory floors or to these edge environments that you looked at? And were there problems there? Like, what was the reason you stepped into the fray and jumped into that market?
So when we looked at, from Autosense perspective, it was a natural tendency to move like, all right, where is the best use case for audio? And we moved into predictive maintenance and applied.
Okay.
I looked around, and we were the first one to solve for edge thing. Everybody else was, they put the moat on and they send everything up to the cloud and they do the processing in the cloud, and then they can do a mobility call and send a text message or whatever they would do. That's where I saw the opportunity, saying like, okay, everybody is still doing it in the cloud. And Autosense, we figured it out, but we were very narrow in the solution space that we were providing. How do I make this as a generic platform available for everybody else can come and operate? So hence, Latent AI was born.
Okay, and now you guys have a couple of things you're developing, and they're developer tools, right? Is that correct?
Yes.
I think you walked me through 3, so maybe if you could just kind of talk about what those are.
Yeah, so we have, so our platform is called Latent AI Efficient Inference Platform. We have what we call as LEIP, right? So we have LEIP Compress, LEIP Compile, and LEIP Adapt are the 3 main products that we've come out with. And of course, we're continuing to build different modules under each one of them and adding other modules as well. And LEIP Zoo is there. Zoo is basically the collection of models that we have tested and samples that we give customers to test. So remember, originally we were talking about the millions and millions of parameters in a neural network and an AI model. So what Compress does is takes those millions of parameters which are expressed in 32-bit floating point, and we convert them into 8-bit integer and below. We can take the value and represent it all the way down to 2-bit and 1-bit. So we can compress the model by almost 10 to 12x in size without losing much accuracy. With AI, it's always about predictive behavior of the model, right?
Right.
It's never an absolute value. It's an approximate value.
Right.
This is an ongoing joke in the deep learning community, right? What is 2 plus 2? In absolute math, it's 4. In the deep learning world, it could be 3.964, something like that, right? So
it's 4 with a confidence rate of 85%.
Something. It is never 4. It is never 4.
Right.
It is never 4.
It's near 4.
3.96 with about 90% accuracy. So that's the confidence.
Okay.
So we try to reduce that confidence level by giving it a delta of about 2% from the original model. So the original model is like, say, 95% accurate. We try to shrink the model in size and maintain it up to about 93, 94%.
So back to the sort of the factory example, let's keep using the prior example. So essentially, instead of taking all the sound data, shipping it up to the cloud and running it through a larger model and getting it, let's say, a 95% accuracy where it can predict, hey, these brakes are likely to be bad and we should replace them now, you're able to say, okay, let's compress that thing 10x. So it's 1/10 or 1/12 of the size, run it on a local, whatever, PC or something small, and then have it make a prediction that is almost as accurate, maybe 94%.
Exactly. And with this, not even a PC, right? If we can compress that particular model so far down, we can actually run it on the sensor.
Oh, wow. Okay. So that now we're talking really
data
compressed.
Coming out of this,
yeah,
exactly. Coming out of the sensor, you're getting an intelligent information rather than raw data.
Okay, so the sensor then can do the hard work of the sensing and literally just output a message that says this thing needs to be replaced, and then the system can go from there.
Exactly.
Okay, great. Exactly. And so you've got Compress, which it sounds like it compresses the model.
Compresses, yeah. And then the compiler piece, which is basically our pipeline. You got the smaller model now. We take the smaller model, put it through our compile process, and you get an executable model at the end of it, an executable object file. So our compiler targets GPUs, CPUs, x86, DSPs, microcontrollers, AI accelerators, FPGAs, any hardware fabric you think of, we can target and compile the model down.
And let's pause on that just for a sec, because my understanding, and again, correct me if I'm wrong on this, but I thought that essentially if you were, let's say you were the developer of this application and you're writing it for the cloud, and then someone said, oh, I also want you to write this model, fit this model on this small sensor out in the factory, they would say, one, I don't know how to compress it to make it fit, and two, I don't know anything about that piece of hardware. And if you say, run it on these 20 different sensors in these 30 different, 20 different environments, they would say, I quit and go somewhere else. Because those are things they don't know how to do. They don't understand those platforms. Is that pretty accurate?
Exactly. You hit that, Troy. So we call this the chasm, right? So you got the AI engineers who know all about the model and the data scientists that are helping them build the model.
Right.
And then you have this embedded guys who have no freaking clue about the AI side of things.
Sure.
They finish the model, throw it over, and now go figure it out.
Yeah.
So the only way that now folks are doing it is all right, let me take a guillotine and chop, pruning the network, reducing it in size by basically throwing away information that they've learned. And then now and then they try to force fit it, and they try to work with their hardware vendor to get the right tools and then put it on to the target hardware wherever they go.
Okay.
We simplify that process for them.
Got it.
We bridge the gap between the two guys. And another thing that we do during the compress process is, if you have a hardware, and the target hardware's device constraints, like what's a compute and what is a memory availability, bring that into the training cycle where our libraries sit. We can use that information to compress it further and help you design your network according to your target hardware.
So as long as you know what those endpoints are in advance,
yeah.
And those hardware platforms, and again, like you said, they could be a variety of different systems on a chips or whatever.
Exactly.
As long as you know that in advance, you can somewhat custom build your model at the center so that it will be more compressible and be able to be delivered to those hardware targets when you're done.
Exactly.
Okay.
Exactly. And one of the options we do provide there is we can give you a design table. You want this size model, this is the accuracy you're going to get. If you're going to get this size model, this is the accuracy. We'll give you a design table. You pick which is right, which needs to go where, and you can deploy.
And as the builder, if I'm the vendor in that case and I'm producing that application, then that seems super helpful because you're giving me the choice, and then I can make the choice and say, oh, actually, I really don't want to have it be that low accuracy. I'm going to have to buck up, and I'm going to put a slightly heavier piece of hardware in that function on that factory floor. But that's a trade-off they're willing to make because they know what that cost trade-off is.
Exactly.
Okay.
And finally, some of the semiconductor customers that we have are using us to design their chip as well, in the sense of how many models can I fit here? What operations do I need to support based on the models that we are able to compress and give them?
So let's talk about that for a sec, because I think that's a really interesting emerging area is these AI chips. Yeah. And there's a huge race on, it seems like every day, yes. There's a news story, new AI chip. And some of the names are brand new. And you keep seeing, obviously there's NVIDIA and kind of the standard ones that have been around for a while, but there are so many new ones coming up. It seems like there's an explosion of AI chip vendors.
So we actually, funnily, we are talking to many of these early stage startups in the semiconductor space for AI accelerators, and they feel relieved after talking to us because they don't have to solve the software side of things.
Got it.
There's there are two people in a garage here in San Jose, right? They came to us and they got some NSF funding, and then they're building. They got a good architecture, no questions about it from a hardware perspective. They were pulling their hair out, and then the guy talks to me. He finds me in a random networking event, and he's like, "Your God sent to me, Jags." And then we get a technical meeting together, and we are getting our first tape out done. And we are so happy that we found you because we don't have to change anything in our tape out because we can just overlay your network onto us.
So at the end of the day, you guys are working on which industry segments? Are you working in autonomous vehicles or surveillance or remote monitoring and predictive maintenance, location, energy management? What areas, or do you care? Are those sort of any of those?
It's any and all of those, right? The beauty of being a developer platform and solving something that's very, very up and coming, right? Like state of the art technology, if you were to call it, cutting edge technology. No pun intended on the edge. We have been pulled into all sectors, right? We are, from a layering perspective, I'm working with semiconductors, as we just spoke about, but we're working with OEMs, we're working with automotive OEMs, we're working with industrial equipment OEMs. They're building, they've got a fixed bill of materials and they need to add features to it. And we are helping their developer teams to push some of the edge models, AI models down to the chip. And automotive OEM, we've got a camera system identifying objects in a backup camera, and we are in discussion with an ADAS system about segmentation and running certain models at a higher speed, a higher frame rate. Right? So we can get there. Then the third layer we are talking to is the telcos as well as the CDNs. These are all sitting on the network edge, right? And they are the entry point into the internet, and they can provide the lowest latency possible on a connected world, right? From a telco point of view, in their 5G ecosystem, they want to offer new services around 5G and AI. And we sit right in the smack middle of their multi-access edge compute platform, the MEC platform, and provide AI acceleration services there. We can provide tools for developers to bring models to run on there, and then we can make that models run faster on the platform. Right? CDN's the same thing.
Can you give me just an example of what application that would serve? And correct me on this, but it sounds like, okay, the old way would be put the big model at the center, let's say the data center of the cloud. The edge way would be to put it all the way out at a device, let's say a sensor in a factory. But you're really talking the middle case. Let's say there is a sensor on the factory, but it has a 5G chip and it's communicating back through the telco network. You're saying it doesn't have to reach all the way through the telco network and all the way back into the data center. It can actually hit the edge of the telco network and have some ability to call some technology there and run a model there. Is that right?
Yeah. So here's a simple example, right? Think of analog gauges across all the different factory floors, right? Even in oil and gas perspective, right? Most analog gauges are useless. Right, they give certain information. They're not very critical from an operations perspective, but some are very, very critical. Pressure gauges and flow meters, for example, can be
super
safety critical. Instead of digitizing them, which could be an expensive and an intrusive process, companies are coming up with a solution of putting a camera in front of it and reading the thing. What we have figured out is, like, from a camera perspective, we are able to isolate, normally they don't put one camera in front of things, they're going to put it in front of a bunch of things. So from the camera perspective, the first layer of edge can isolate all the dials separately. Send it up to the MEC over 5G, and at the MEC layer, we can do further compute in figuring out where the needle is, and based on other information from that meter, what the reading is.
Because that's too heavy weight to do computationally. It's too expensive to do at the edge, inside the room where the camera is.
Exactly.
Okay. And latency-wise, you don't want to do that all the way back at the cloud. You might be adding another 30 to 50 milliseconds, and if it's a flow meter and it's a $10 million accident, if that flow meter hits red, you can't incur extra latency in making those decisions.
Exactly.
Okay.
Exactly. And then the 5G deployments are going to be local to the factory or the plant, right? Even the physical latency is also reduced drastically. And then the fourth layer is we are working with application developers. The app developers that want to bring AI models for different applications, and they are very constrained with the power budget. We can help them bring it down and run it efficiently wherever they want.
So it sounds like you have no shortage of dance partners to work with in the ecosystem. Yes. Across every sector, which is great.
Yeah, the problem is choosing the right one.
Right. Yeah, I mean, it's a very horizontal piece of technology. So which sectors, which geographic regions, which players in each sector. So I bet that's probably an ongoing discussion with the management team in there.
Absolutely, absolutely.
So
Everybody's excited. Everybody wants to work, right? So it's a good place to be.
It's a great place to be. And the market growth, I was looking up some numbers this morning, and it looks like they're kind of talking about edge AI being kind of a 20 to 25% compound annual growth rate right through till 2026. So there's a ton of stuff. The pie is growing very quickly. There are a lot of folks in this space. There's Exnor and Swim and Tibco, and of course IBM, Google, Amazon, Microsoft. Who do you mostly think is your biggest competitor?
So I would say, from a competition point of view, if you just look at it through one lens, it's going to be Google from a TensorFlow perspective and PyTorch and open source Facebook type of thing, right? So that's one bucket of competition you can look at because they're providing these tools for free. Google does quantization compression up to 8 bits, but their focus is always on trying to get their TPUs capable, right? They focus on running it on TPUs.
And just to pause you there, so the TPUs being their hardware accelerator chips that they've custom built.
Exactly.
Yeah.
Exactly. So most of the TensorFlow compilation work is targeted towards that. You are not going to get full support for other accelerators. Even like if you're getting these new AI accelerators coming in, they will not get that time of the day from Google to support them.
Right.
Right. So those are the places that we help, and also existing hardwares that can help us. The other competition that I would look at is Intel, Qualcomm, NVIDIA, right, and ARM. These are all vertically integrated tool providers, right? But you're stuck with their hardware, and whatever they're doing, yes, they have far reach into their hardware compilers to provide certain optimizations, but then you're stuck within their ecosystem. You're not able to come out. We provide that horizontal capability. Right? And then I didn't talk about LEIP Adapt. Right? This is where we differentiate from everybody else. We talked about millions of parameters, and you need to run every million parameter for every inference that you do. We have figured out a way that you can run only 20 to 30% of the model, of the neurons, and still get good inference and throttle it up and down as you need, just mimicking how the human brain works.
So use more or less of the neural network neurons based on a case-by-case basis.
Yes.
Which
and
then means you can
dynamically
be more efficient with your power budget.
Exactly. And also inference speed. Right? If you don't have to execute a million parameters, you're only executing 300,000 or 200,000, you're almost 1/3, 1/4 faster.
So it's faster, it's less power expensive, and it's still almost as accurate. So you might get a little drop in accuracy compressing the model and delivering it to the edge, maybe another little tiny bit of accuracy drop if you're using less of that edge-based model and running 1/3 of it or 1/4 of it. And so those are just trade-offs that app developer could make in collaboration with you.
Exactly.
Okay. This is great. I think we have a pretty clear picture of what's going on in the space. So I'll try and summarize it poorly, and you can build on it. But it sounds like essentially developer tools. Oh, and one question I had on that is: are you also doing training, system integration, things like that, and providing that level of support to these folks?
So we've realized that as we are going to customers, AI field is still very nascent, right? So you don't have many expertise available on the customer side. There is some expertise. So we are providing more of a consulting service in helping them with their models. But then we have system integrator partners that we want to, and we are open to that as well, right? New SI partners, we are happy to welcome into our fold and have them try our tools and take it to their customers as well. So there are use cases that our customers are coming to us with a full stack solution that they want to be built. And we don't do the full stack. We just do the AI piece, and we want to bring other experts in that field to package it up.
Right. I mean, my favorite line on this that I've been having this conversation about lately is, don't forget all the other stuff around the AI that is actually the rest of the product. And that seems
Exactly.
like if you're going to access all of these customer segments, I mean, your team can't speak the language of every single industry and every single geography. That's not possible, but you can certainly talk to a lot of service providers and system integrators who know those sectors and those domains really well and have those customer relationships and are building those big complex apps. So that makes a lot of sense.
And then the way the platform is built is to enable those complex system integrators to profit as well. Like, it's a developer tool. It's a horizontal play. You can go build your vertical use cases and vertical applications on top of it, and you don't have to retrain your staff on the expertise on the underlying tool. Right? It's the standard, and you can just transfer your industrial knowledge and apply to each vertical and profit from that.
Which is great because you're taking away the requirement for them to understand all of these new and emerging AI chipsets, system on a chip, sensors, all of these things that are in the marketplace today or tomorrow. They don't have to know all that. You're managing all that. You're kind of abstracting that away so they can focus on the domain expertise. Yeah, that makes a ton of sense. Who should be reaching out to connect with you? In other words, what size of customer, what stage of customer, what type or size or scale of project? I'm sure if a homemaker is building something with a Raspberry Pi in their garage, that's probably not a customer for you. But if they're building a car, they probably are. So, kind of, what's the range? How would people decide whether they should be talking to you or not?
So first of all, as I initially mentioned, right, we are backed up with a lot of customer engagements right now. The team is very small. I'm doing this very methodically, trying to prove certain areas, and then go and accelerate the customer adoption on the other side. What is interesting for us today is more from an industrial point of view. Right? We have a couple of customers in the quality assurance or predictive maintenance side of areas. We would like to see more of those customers now to get a taste of what's going on there. The data, they have the data. We are not asking for their data. They can bring the data. If they have AI engineers in-house, well and good. If not, you have a data science team, or if not, that's not a problem either. But you have a problem and you have the data, you need us to help. We can help there and bring a model that can help you with whatever that problem may be. Right? So industrial would be one primary target area that we're looking for.
So industrial and manufacturing as a sector, and predictive maintenance as kind of a use case is a hot spot. Anything else?
Predictive maintenance, quality control.
Okay.
Yeah. And then this is the third area that's popping up here and there is like workflow automation from an operator supervisor perspective. Right? All these operators are standing there doing their work, and end of the day, they fill in a report. Can we make that more on an automated basis? Like give them like a clipped audio recorder that they speak, and we can run an AI on the edge that does the NLP conversion of speech to text, and they don't have to come and sit and type or write on a clipboard every 2 minutes.
Right. So you're really trying to make their workflows more efficient and the reporting more real time, or just less work?
Less work and more analytical as well, right? Like a plant manager doesn't need to sit and read 600 reports in a day to figure out what happened. Or he's like the supervisor needs to read 8 reports to summarize his report. All of this can be automated and brought together. And of course, the supervisor still looks at it and validates it for any inaccuracies, and done. It's a 2-minute work rather than a 20-minute work.
Got it. Okay, so industrial and manufacturing, and then multiple use cases inside there. So anybody in that space who has a business problem to solve, has some data, they may or may not have a data science team, they may or may not have tried to use AI, which may or may not be the right tool for the job, but they can be anywhere in that journey in terms of their own maturity level, and at least come and have a conversation with you.
Exactly.
Okay. What's the best place to track you down?
LatentAI.com.
Okay, and I'm going to put that in the show notes, of course, and those will be distributed everywhere on YouTube and Google and Spotify and Apple and all of the usual places. Okay, well, that's great, Jags. I want to thank you so much for coming on today. This has been really cool. It's been great getting to know you over the last couple of weeks of conversations and better understanding what you're doing. Thank you so much for making time. I know you're super busy, so I really appreciate it, and I'm sure this will be helpful to people who are listening. So thanks for being here.
Thank you, Troy. Thank you, Troy, for having me. And it was such fun talking to you. And talking about Edge always brings sparkles into my eyes, right? So thank you for having me and giving me this opportunity.
Yeah, you're very welcome. So that wraps the show. Thank you very much, everybody, for joining us on the Productive AI podcast today. That was Jags Kandasamy from Latent AI. And see you on the next show. Thanks for watching.